Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 6.3 from your textbook, which introduces you guys to the second method for calculating volumes of solids of revolutions. In this video, we're going to introduce this second method called the method of cylindrical shells, and we're going to take a look at a couple basic examples of it. As we sort of saw in the very end of the previous video, where we were sort of wrapping up talking about the disk and washer method, we saw that one of the major limitations of only having one method for handling volumes of solids of revolutions is that we're sort of restricted to having to work with the particular variable. We saw that when working with disks and washers, right, if the axis of revolution is horizontal, then we must work dx. And if the axis of revolution is vertical, then we have to work dy. And in our very last example, we saw that that can be a little bit messy. So this method of cylindrical shells allows us to sort of reverse that. In other words, if we have a vertical axis, the method of cylindrical shells is going to allow us to work dx, whereas if we have a horizontal axis, the method of cylindrical shells is going to allow us to work dy. So to see this, we're going to start in with a little bit of a sort of visualization and explanation. We don't have to be quite as thorough as we were when we were doing disks and washers, because we have the general idea now that if you integrate an area, you create a volume. So we won't have to go all the way through that sort of Riemann sum approach, but I do want to sort of let you guys sort of see where this method of cylindrical shells is coming from. So let's talk about our setup here. So we're going to suppose that we have an area or region under a function f of x and above the x-axis from x equals a to x equals b. So our sort of standard setup. But we're going to revolve this solid this time, instead of around the x-axis, around the y-axis. So a vertical axis of revolution. Then the statement of the formula for the method of cylindrical shells says that the resulting solid can be determined by the integral from a to b 2 pi x f of x dx. And I'd like to sort of go through and see exactly where this formula comes from. So let's go ahead and give ourselves a diagram of sort of the situation that we're talking about here. So there's our axes. We have some function f of x, so we'll just draw some arbitrary function like that. We're working from a to b there, so those are the sort of ends of our region. So the stuff under this curve and above the x-axis is the area that we're revolving. So we have all this stuff in here. And this time our axis of revolution is this vertical axis. So if we did want to go ahead and just draw the sort of mirror image, so we have a sense of the object here, we'd have something like that. And then we'd have our piece that goes over there, and we have another piece there. It looks a little rough. Let's just go ahead and redraw that real quick. There we go. That looks a little bit better. Again, doesn't have to be perfect. It's just an estimation. But there would be the mirror image when it comes out. So again, keep in mind that this guy is coming around like this out of the page, then coming back into the screen, and then going back behind it. And then, of course, if we were sort of indicating the piece, there would be this sort of hollow center in here. So again, you would be able to sort of go through this. But there is actual volume being created by sort of revolving those pieces around here. So again, we sort of have this weird, almost like a curved bracelet type shape where you could put your arm or something through it, but you'd actually have some volume around it. Okay, so what we're trying to do here is normally we'd be sort of forced to work on this from the y perspective, because our old method would say, okay, we'd start from our axis of revolution. We'll zoom in a little bit as we talk about that. We'd start from our axis of revolution, we'd draw across, then we'd get our mirror image. That would be the sort of inner radius. Then we'd go across here, and that would give us our outer radius, and we'd have some sort of washer shape that we would then have to integrate to build our volume. What we want to do, though, is we want to be able, instead of working from that sort of y perspective across, we'd actually like to look at this from the x perspective. So let's draw ourselves a selection of x and then see what happens when we actually revolve that. So remember, a choice of x is basically choosing a vertical line. So there we go. That's a vertical line that always has the same x value. And let's imagine what happens when we revolve that. Well, what happens is it would end up over here, and it would create a shape that sort of looks like that. Now, because we are just revolving that line, this is a hollow shape. It's a shell. In other words, it's a cylindrical shell, which is where this sort of name comes from. So if we pull this out, right, what this would actually look like is it would sort of look like a cylindrical shell shape. And this would be a shell. Now, the reason that I'm stressing that it's a shell is because the idea in this cylindrical shell method is that we're stacking these shells together to build the sort of shape. So what you want to sort of think about is if you've ever seen those sort of like Russian dolls that sort of stack together and fill in a full volume, that's what we're sort of doing here. So our first shell would be this sort of empty shell, and then we'd have another shell that would be a little bit wider and a little bit taller. Then we'd have another one that would be a little wider and a little taller, and another one that would be wider and taller. And when we stack all those shells together, put them all inside of each other, we would build our overall volume here. So we know then that if we can figure out the area of this shell, right, then if we can integrate that, then that'll give us our volume. So what area are we talking about here? Well, as a three-dimensional shape, the area would be the surface area. So we're talking about the surface area of that shell. So if we talk about the surface area of this shell, well, what's the surface area of a cylinder? Well, we know that that surface area, if you think about it, it's each of the sort of circumferences of these circles and then add it up. So if you might know that formula, that's just 2 pi RH. Right? So the surface area of a cylindrical shell is 2 pi times the radius times the height, which again, the radius would be this here and the height would be this here. So in terms of our selection, can we talk about this radius and this height in terms of our information here? Well, if we imagine that this is sort of an arbitrary x sub I star, right, just some random choice of x, we can actually phrase both the radius and height in terms of our function and this xi. Let's think about this radius. The radius is this distance here, so it's the distance from our choice to that axis. Notice that that is exactly just that xi star. So we know that our radius is going to be that choice of x, that xi star. And then the height, of course, is from here up to here, which is our function. So the height would be that function at that xi star. So that tells us that the surface area, if we were to write it out in sort of terms of the x and the function, would be 2 pi xi star f of xi star. Then, of course, right, if we have that, if that's our surface area, then if we stack all those areas together, right, that gives us approximately what our volume is going to be. If we then actually take that as a Riemann sum, again, we're not going to go through the full Riemann sum derivation here, but this would be converted into our actual integral. So this would tell us that the integral should turn out to be an integral of 2 pi x f of x. And if we look back, that is exactly the sort of formula that we're getting, where we're choosing that x from x equals a to x equals b. And that's exactly the volume formula that this is stating here. So the idea behind this cylindrical shells method is, you can really think about it in two ways. One is that we're developing this method so that if we have a vertical axis, we can still work with respect to x. If we only ever learned the method of disks and washers, then every time we had a vertical axis, we'd be forced to work with respect to y. But this method now allows us, if we have a vertical axis of revolution, to work with respect to x. The second thing that's sort of unique about this method is that instead of building our shape by sort of stacking together a bunch of washers, a bunch of those sort of donut shapes together into slices and then putting them all together to build a volume, now what we're doing is we're stacking together a bunch of hollow cylindrical shells. And once we put all those hollow cylindrical shells together, that builds our volume. So in a lot of ways, these two different methods, disks and washers and cylindrical shells, even though they're both calculating the volume of a solid, they're really doing it in different slicing methods. Sort of in disks and washers, you're slicing it into these donut shapes and then stacking the donut shapes on top of each other. And for cylindrical shells, you have a bunch of hollow cylinders that you put inside of each other to make the resulting solid. Okay, so this was just a quick visualization and explanation of where this formula comes from. Again, we can do this also if we have a function of y and we're going around a horizontal axis. So let's talk about that real quick. So an analogous argument, which we'll just write out real briefly, would say that if we have an area or region between a function that is a function of y and the y-axis, from y equals c to y equals d, and we revolve around the x-axis this time, so a horizontal axis of revolution, then a similar formula, 2 pi y times g of y dy, will give us the volume. Let's just visualize this real quick now that we have the general idea. So if we take sort of an arbitrary curve, maybe we have something that looks like that. So there's our g of y, and we're working from y equals c to y equals d. So there's the ends of our sort of region like that. And of course, we're talking about it between the y-axis and that function. So the region that's in discussion here is this. And now we're revolving around the horizontal axis here. So we're revolving this way. We can zoom in a little bit, have a better look. So that's going to create something that looks like that to there. And then that to there. And then we'll have something that looks like that. So there we go. There's our mirror image there. Okay. And so again, there's sort of the internal part that would stay hollow. And then there we go. Okay. So there's our region. There's its mirror image. There's an attempt to sort of visualize in 3D what the shape is going to look like. So here, what we would be doing is that we're going around this horizontal axis, but we want to work dy. So we're selecting a typical y value, so something in here, drawing across like that, reflecting that down to here. That is creating the shell. Notice that this time the shell is on its side. So if we cut that out, the shell is sort of going to look like that. So now the shell is on its side. This time is the height, and this distance from here to here, that is our radius. Once again, we could look at the surface area of that thing as 2 pi rh. If we choose sort of that typical y value, yi star, well, then that radius is the measurement from here up to that yi star. So we could say that the radius is just that yi star. And the height, well, the height is this way. So it's from here to our function. So that's just our g at that yi star. So that means that the surface area of each individual shell is 2 pi yi star g of yi star. So if that's each piece, we could sum those together to get a rough approximation. Then we could we could actually integrate and put them all together since they're infinitesimally thin. And then, of course, this would give us our formula here, where this would convert to 2 pi y g of y. And, of course, the selections for y could run from c up to that d. So that's where this integral is coming from. Notice it's exactly the same argument we did in the first part, just now sort of from the y perspective, and those shells are going to be laying on their side. Okay, now, as you guys know, when we're working on these solids of revolution, we don't want to be just restricted to these basic cases. We also don't want to be restricted to only being able to revolve around the x and y axis. So before we get into some examples, I want to just give sort of that summary of really understanding why, even though we talked about two cases here, really this method of cylindrical shells can be thought about as one general method here. So let's go ahead and talk about a summary of this and then look at some examples. So, in general, when you guys are working with the method of cylindrical shells, you should basically think about it as follows. The sort of general formula is that the volume can be found as doing 2 pi times the radius times the height. That's what each of those formulas were doing. It was 2 pi times the radius times the height. And then you choose the variable of integration as follows. You will notice that cylindrical shells is performed dx when the axis of revolution is the y-axis, a vertical axis. So any axis parallel to the y-axis, you'll do cylindrical shells dx. And cylindrical shells is performed dy when the axis of revolution is the horizontal axis, the x-axis, or any axis parallel to the x-axis. You will notice that this little portion here is exactly the opposite of what we did with discs and washers. So this tells us that regardless of which axis of revolution we're using, we can always choose a method that allows us to work dx, and the other method will allow us to work dy. And we'll investigate that a little bit further in the next video. But for now, what I'd like to do is look at just a couple examples of just strictly using this method of cylindrical shells. So let's jump into those. So here we go. We've got our first example here. We want to try to determine the volume of the solid created by revolving the area under this curve, x squared plus 1, and above the x-axis from x equals 0 to x equals 2 around the y-axis. So let's go ahead and see if we can do that. So there we go. And we'll draw ourselves our axes. We'll sketch this thing from 0 to 2. So I guess we can go 1, 2. And we'll have to go 1, 2, 3, 4, and 5. So x squared plus 1 is just a standard sort of parabola, but raised up. So we've got there, there, and there. So there's our parabola piece. And then we're truncating it there and there. So we'll sort of zoom in a little bit. And there we go. And we're revolving around the y-axis. So we're going this way. So I guess the sort of mirror image, if we wanted to, would be here and here. And right there and right there. So again, our region is this stuff in here below our curve and above the x-axis. So it forms this thing here after being revolved, and there we go. So once again, this would sort of be forming a like a tumbler type shape. Again, like this one would not actually be able to reach through because this is solid down here. So you could fill this stuff with some sort of liquid or something, and you'd actually have some volume on the outside where you could, you know, hold the glass, so it would actually work as a glass here. Okay, so if we were going to do this with respect to discs and washers, our original method, we would then need to think about everything in terms of y, because if you have a vertical axis of revolution and you want to use discs and washers, you have to work with respect to y, which would mean that we would have to solve for this in terms of y, and we'd have to think about everything in terms of y bounds. And if you think about that, that would be a little bit messy, because we'd have to work from 0 to 1, and then we'd probably have to work from 1 up to 5. But with our new cylindrical shells, we should be able to do everything in terms of x. So we want to try to use cylindrical shells here. And since it is a vertical axis, cylindrical shells is going to be done using dx. So let's draw a typical shell here. So since we're going to be working dx, let's choose a random x value. There we go. That's what it would look like in our region. When it gets revolved, it would come over here, and there is where that sort of shell is given. And of course, that component of the shell is its height, and that component there is the radius. Okay, so we're ready to actually go ahead and set this up. The volume is going to be the integral. These x values could have been selected anywhere from x equals 0 all the way up to x equals 2. So we have the integral from 0 to 2, 2 pi. What is going to be our radius? Well, the radius is measuring from here to whatever our selection is. Our selection is just x, so it'll be 2 pi x. And then what is the height here? Well, the height is our function, which is that x squared plus 1. So we'd have x squared plus 1 dx. Does that match what the sort of general formula said? Yeah, it said it should be 2 pi x f of x, and that's exactly what we have there. You might say to yourself, why didn't we just write in the formula? Well, again, that formula is going to start to break down a little bit if we had a non-standard axis of revolution or something like that, or the area between two curves. So I do really recommend always doing it from the visual perspective of drawing in the typical shell, confirming the radius, and confirming the height. And we will see that that will begin to be important as we do some more advanced examples. Now, this one did say determine the volume, so we actually do need to evaluate this. This is a product, and in general, integrals and products do not mix together very well. So we need to sort of multiply this out so that we can integrate the pieces separately. So if we want, we can factor out the 2 pi and get the integral from 0 to 2 of x cubed plus x dx. Then we can go ahead and actually integrate that. We have 2 pi, and we get 1/4 x to the 4th plus 1/2 x squared. That's just two uses of power rule, and then from 0 to 2. And then if we do that, we get 2 pi. We can plug in the 2. looks like we would get 16 divided by 4, so 4 plus 4 divided by 2, so 2, and then minus when we plug in the 0, we're just going to get 0. So this volume looks like we're going to get 12 pi overall. If we were careful about units, I'd suppose it'd be units cubed because it's a volume. But again, in this class, we're not going to be really worrying about units like that. So just saying 12 pi, totally sufficient there. Do keep in mind, though, that even though it wasn't a particularly hard integral, this cylindrical shell formula, because it has that radius times the height, is often going to involve then multiplying this out, because, again, we can't integrate products, but we can integrate a sum by just integrating each piece separately. So you are going to usually have to multiply this out if you actually need to determine the volume. Okay, let's take a look at one more sort of basic example of this. So for this one, we are going to have a non-standard axis. So what we're going to do is we're going to determine the volume of the solid created by revolving the area between x equals 1 over square root of y and the y-axis from y equals 1 to y equals 4 around the axis y equals -1. So let's start by drawing this thing in first. So there we go. Notice that it is going to be a non-standard axis. It's not just the x or y axis, so we'll have to be a little bit more careful with the radius. Anytime you have a non-standard axis, you're going to have to be a little more concerned with the axis of with the radius. So let's go ahead. We'll put in 1, 2, 3, 4 for y, and then I guess like maybe 1, 2 for x. There's y equals -1, so we can label in our axis of revolution real quick. That's y equals -1. X equals 1 over root y maybe is not a standard function that we're used to, so let's just plug in some values. At y equals 1, you're going to have x is 1, so I guess it's right here. And then I suppose when y is 4, you're going to get 1 over square root of 4, which is 1/2. So I guess it's back over here, and looks like our curve is going to look something like that. What region are we talking about? Well, it's tempted to like fill this in below, but remember we're actually working from y equals 1 to y equals 4. So we're actually working this way with the y-axis. So we have that region. So if we zoom in a little bit further, our actual region that's being revolved is this stuff here. And if we want to go ahead and fill that in, we'll need 1, 2, so 1, 2. And at that point, we'll come here and here, and then we'll need to go 1, 2, 3 more. So there and there will be those ones. So there we go. There we go. So that's going to be our symmetric image there on here. And there we go. If you like the 3D component, certainly feel free to do so. In the future, I'm probably going to stop drawing in the 3D thing because I find that it makes it a little messy. I prefer just the region and its mirror image. But let's go ahead and try to actually go through this. So we're going to use this new method, cylindrical shells. We have a horizontal axis this time, right? Y equals -1 is similar to the x-axis. It's a horizontal axis. So with cylindrical shells, that means you're going to be working dy. Notice that that's good because that allows us to keep the bounds as we were sort of told and allows us to keep the function as we were told. If we wanted to use distant washers, we'd have to change everything in terms of x. Okay, so we've got this. We're going to go ahead and use cylindrical shells. So let's draw our typical shell here, or an example shell. So since we're working dy, what we want to do is we want to select a y value somewhere in our region. So maybe here. Draw it over there, have it reflect down, so somewhere like there, and we can take a look, and there is our shell. Now notice again, because I went ahead and drew the 3D thing, it's a little bit messy to see that, but we can actually see the shell right there. So this right here, again, shells on their side are always a little bit harder, but this right here, that is our height. And of course our radius is from here down to there. That's our radius. So let's go ahead and write this in then. So our volume is going to be our integral. These selections for y could have started from 1 all the way up to 4. So we'd have the integral from 1 to 4. Then 2 pi. All right, radius. Anytime you have a non-standard axis, you got to be a little bit careful. How should we view the radius here? Well, we know it's going to be based on our choice of y. choosing that y is measuring from here to here, and then we have to go an additional unit to -1. So if you want to think about that as a measurement, you're measuring from y to y equals -1. So that's y minus -1. Or if you were to simplify, that would be y plus 1, which makes sense. You choose your y value, that measures to there, then you add an additional unit to get down to your axis of revolution. So y minus -1. Notice again, by using the negative there, you can actually see the axis of revolution in the formula. The -1 appears right there. Okay, what about the height? Well, the height is here. It's measuring from here to our function. So we know our function is just written as 1 over square root of y. So 1 over root y dy. There we go. If you want to simplify, you could immediately sort of recognize it as 1 to 4, 2 pi, y plus 1, 1 over square root of y dy. In terms of actually integrating this, which we do need to do because it says determine the volume, we can go ahead and multiply this out to start with. So we get that the volume is the integral from 1 to 4, 2 pi. Looks like we should have square root of y plus 1 over square root of y dy, because y divided by square root of y is square root of y. Those square roots might be nice in algebra, but they're sort of hasslesome here. So let's pull out that 2 pi and look at everything in terms of rational exponents. So we can view it like that. Square root of y, of course, is equal to y to the 1/2, and 1 over square root of y, of course, is equal to y to the -1/2. Then we can go ahead and integrate. So, and we'll use some brackets there. I think that's a little nicer looking. New exponent here is going to be 1/2 plus 1, which is 3/2. Put the reciprocal in front, so 2/3 y to the 3/2. Add 1 to this. New power is going to be 1/2. Put the reciprocal in front, so 2y to the 1/2. Evaluated from 1 to 4. Then we can plug that stuff in. We get 2 pi brackets. Let's plug in the 4. So 4 to the 3/2. 4 to the 3/2 is going to be square root of 4, which is 2, and then cubed, which is 8. So that's going to be 16/3. And then, of course, plugging in the 4 here, square root of 4 is 2. 2 times 2 is 4, so we get plus 4. And then minus plugging in the 1, 2/3 plus 2. Could we simplify? Yeah, sure. Do we want to? Probably not. We can just leave it right there as long as we've demonstrated that we understand what it means to sort of evaluate the definite integral. Okay, so this right here sort of is going to be the last basic example for cylindrical shells that we're going to do. And the main reason that I wanted to do this one is just to make sure that you guys know what to do with a non-standard axis. Notice that by having a non-standard axis, this axis that was shifted down here, we had to take that into account in the radius calculation, and it ended up, instead of the radius just being simply y, it turned out to be y plus 1. Does this invalidate the formula that we wrote down at the very beginning? Well, no, because the formula that we wrote down at the very beginning only applies if you have literally the x or y axis as the axis of revolution. With a non-standard axis of revolution, you're going to have to manually figure out the radius. That's why I'm really stressing to you guys about always using the visual approach for determining the height and the radius so that you can fill in this formula. Now, at this point, we've learned 2 different methods for handling solids of revolution: discs and washers and cylindrical shells. In our next video, we're going to do a bunch more examples focusing on setting up integrals for volumes using both of these methods so that we can start to compare and contrast what they both look like, how to identify which method is maybe better, and just being more comfortable with these visualizations. So we've still got more examples to do. We'll be doing ones with both discs and washers and cylindrical shells in the next video.